and engineering practices. Our goals for this section are to understand the intent of each of the 8 science and engineering practices, to distinguish between them, and then to be able to identify examples of these practices in our current curriculum and instruction. There are 2 main resources you'll want to have for this section. If you haven't downloaded these documents yet, you might want to take a few minutes to do that. You'll want to have the PDF or hard copy of the framework available while you do your alignment. The Science and Engineering Practices reference document, I recommend you having that actually out with you right now during the video so that you can write notes on it. This would be a great time to pause and either print a copy or locate your copy of the reference document if you don't have it. The framework authors identified 8 science and engineering practices. These are often just called the practices, and the code we'll use for them in this course is SEP, for Science and Engineering Practices. You can see both here and on the reference document, I've listed the page numbers in the framework so that you can find relevant sections. In this presentation, we'll go over each of the practices. The reference document and framework go into great detail about what the practices look like in general and at different grade levels. We'll walk through one example about how you might use these documents for alignment. The first practice is asking questions and defining problems. The description given of this in the reference document is that scientists ask and refine questions that lead to descriptions and explanations of how the natural and designed worlds work, and which can be empirically tested. Engineer questions clarify problems to determine the criteria for successful solutions and to identify constraints to solve problems about the designed world. Both scientists and engineers also use questions to clarify ideas. Something that's really important for our classrooms is that we're allowing our students to have the opportunity to ask these questions. There needs to be a sense of wonder and a sense that not everything is known. Without that, it's hard for students to engage in meaningful learning. When you're looking at items, you will want to really think about whether the item asks the student to pose a question or to identify a problem. Many problems provide students with questions and ask students to reason about them, but for something to be aligned with this practice, it truly needs to be that the student is generating the questions or defining the problems themselves. In order to help you become more familiar with the reference document, I want to show you one page of the document here and do a quick walkthrough of how you might use it. As I mentioned in the last slide, you really need to be having a student pose their own questions when aligning to this practice. That's not a terribly common test item. However, let's just suppose there was a constructed response item that presented a scenario to students, explained something that they had seen in the world, some phenomenon, and then asked them to pose a question that could be used as the basis to design an experiment. In other words, a question that asks students to write their own testable question. If you saw an item like this, you would want to go to the page in the reference document that has the grade level description statements for this practice. So let's zoom in right now on the elementary statements for this practice. We're just going to look at the top 2. In K2, it says that students will ask questions based on observations to find more information about the natural and/or designed worlds. And in 3 through 5, it says that students would ask questions about what would happen if a variable is changed. I want to point out that at the top it indicates that 3 through 5 would build on the experiences in K2, which means that in 3 you can also ask questions about the natural and/or designed world. So given that hypothetical question I posed about writing a testable question based on a description of some phenomenon in the world, these statements make it clear that that would be a pretty good fit. So I can actually use these statements directly for my alignment. Or I could take these statements and say, this seems like a good fit, and go back to the framework to look at what the author said. And that's why I've given you those framework pages. We're not going to work through a sample like this for each practice, as the structure of the document remains constant for all subjects. However, hopefully this example helps you to feel more comfortable using this document. The second practice is developing and using models. A practice of both science and engineering is to use and construct models as helpful tools for representing ideas and explanations. These tools include diagrams, drawings, physical replicas, mathematical representations, analogies, and computer simulations. Modeling tools are used to develop questions, predictions, and explanations, analyze and identify flaws in systems, and to communicate ideas. Models are used to build and revise scientific explanations and proposed engineered systems. Measurements and observations are used to revise models and designs. One of the things that we desperately need to do as a science community is to expand the types of models we use with our students. Many students' only experience with modeling is the idea of making a model, like the solar system or cells that we see in the ceilings in so many schools. We need to do more than this. I recently was at a presentation where we were given the rule of thumb, if you can eat it, then it isn't a model. It was meant as a joke, but for me it brings home the idea that we need to think further about modeling. On test items, you should really be looking for times when the students either have to create a representation or they have to use a representation to find the answer. Often the presence of a diagram is an indicator that you should think about modeling. However, in some cases, the diagram is there just for show. The students aren't actually actively reasoning with it as they answer the question. The next practice is planning and carrying out investigations. Scientists and engineers plan and carry out investigations in the field or in the laboratory, working collaboratively as well as individually. Their investigations are systematic and require clarifying what counts as data and identifying variables or parameters. Engineering investigations identify the effectiveness, efficacy, and durability of designs under different conditions. Often when we think of planning and carrying out investigations, we imagine a setting very different than a large-scale test environment. But there are indeed questions that are designed to assess students' ability to plan and carry out investigation. Look for questions that ask students to identify investigation design elements that make a strong experiment, etc. For example, we often see questions about multiple variables being tested at the same time or other experimental design issues. Analyzing and interpreting data. Scientific investigations produce data that must be analyzed in order to derive meaning. Because data patterns and trends are not always obvious, scientists use a range of tools, including tabulation, graphical interpretation, visualization, statistical analysis, to identify the significant features and patterns in the data. Scientists identify sources of error in the investigations and calculate the degree of certainty in the results. Modern technology makes the collection of large data sets much easier, providing secondary sources for analysis. Engineering investigations include analysis of data collected in the tests of designs. This allows comparison of different solutions and determines how well each meets specific design criteria. That is, which design best solves the problem within given constraints. Like scientists, engineers require a range of tools to identify patterns within data and interpret results. Advances in science make analysis of proposed solutions more efficient and effective. Be careful with this one. Often, when we see a data table or chart, we jump to the conclusion that this would be the practice. But sometimes, like the images, the data on the test is just for show. When test items are calling on this practice, it will ask the student to go beyond just referencing a chart. It will ask them to do some analysis or interpretation of what the data means. Sometimes you can have a question that asks students to analyze and doesn't have a data table or graph at all. Instead, there can be a description of data. Think of a story problem about the weather. If the question asks them to treat the description as data and reason with it, then this is the skill being drawn on. The next one is using mathematics and computational thinking. In both science and engineering, mathematics and computation are fundamental tools for representing physical variables and their relationships. They're used for a range of tasks, such as constructing simulations, solving equations exactly or approximately, and recognizing, expressing, and applying quantitative relationships. Mathematical and computational approaches enable scientists and engineers to predict the behavior of systems and test the validity of such predictions. Yes, when you see a need for students to use math, it's a good bet you should at least consider aligning to this. However, be careful. We are really looking at computational ways to understand the phenomena in the world around us. This doesn't always look like a math equation, and sometimes when we're looking at a math equation, we aren't really using the math to understand things. Always stop to think about why we are using math and how it's impacting understanding of the world around us before aligning to this practice. The end products of science are explanations, and the end products of engineering are solutions. The goal of science is the construction of theories that provide explanatory accounts of the world. A theory becomes accepted when it has multiple lines of empirical evidence and greater explanatory power of phenomenon than previous theories. The goal of engineering design is to find a systematic solution to problems that's based on scientific knowledge and models of the material world. Each proposed solution results from a process of balancing competing criteria of desired functions, technical feasibility, cost, safety, aesthetics, and compliance with legal requirements. The optimal choice depends on how well the proposed solutions meet the criteria and constraints. Many questions that draw on this practice are open-ended. Be careful, though, to be sure that students are being asked to explain a phenomenon, not just explain their answer. And be sure, with designing solutions, they're designing a solution to a problem. When a student is making a claim and explaining why they believe that, we're looking at the next practice, argumentation. Explanations are about demonstrating our understanding of the world around us, not providing reasoning or evidence for our claim. Which leads us directly to engaging in argument from evidence. Argumentation is the process by which evidence-based conclusions and solutions are reached. In science and engineering, reasoning and argument based on evidence are essential to identifying the best explanation for a natural phenomenon or the best solution to a design problem. Scientists and engineers use argumentation to listen to, compare, and evaluate competing ideas and methods based on merits. Scientists and engineers engage in argumentation when investigating a phenomenon, testing a design solution, resolving questions about measurements, building data models, and using evidence to evaluate claims. In order for a question to align to this practice, it's important that students are providing an evidence-based argument. Most often, this will require an extended response type question. However, it's possible to have something that gets at this with multiple choice, especially questions that ask students to identify the appropriate evidence for a specific claim. Clearly, this is assessing one part of this larger practice. However, it would still align here. Finally, obtaining, evaluating, and communicating information. Scientists and engineers must be able to communicate clearly and persuasively the ideas and methods they generate. Critiquing and communicating ideas individually and in groups is a critical professional activity. Communicating information and ideas can be done in multiple ways, using tables, diagrams, graphs, models, and equations, as well as orally, in writing, and through extended discussions. Scientists and engineers employ multiple sources to obtain information that's used to evaluate the merit and validity of claims, methods, and designs. This is a really huge practice. There's so much within this. As you think about your alignment work in this practice, I'd caution you not to let this umbrella get too large. It can be tempting to stretch this to cover any question that didn't fit elsewhere. But before you align to this, ask yourself, if a student gets this question correct, does that really tell me about their ability to obtain, evaluate, and or communicate information? Why? How? If you don't have an answer to that question, then it probably doesn't align here. And that's a great question to ask yourself about all of these. Anytime you're aligning to one of the practices, ask yourself that question. If a student gets this correct, what do I know about their ability to use the practice I'm aligning to?